We will now discuss the parallel axis theorem. The parallel axis theorem gives us a method of finding the moment of inertia of an object about any other axis other than the axis that passes through the center of mass. For example, you know that the moment of inertia of a disk about an axis that passes through its center of mass is 1/2 mr squared. Is that right? Okay, if you know the moment of inertia about an axis through its center of mass, then you can find the moment of inertia of that object about any other axis. As long as you know the perpendicular distance between the new axis and the axis that passes through the center of mass. Alright? And that is what parallel axis theorem gives you. Alright, let's have a look what parallel axis theorem says. If I center of mass for an object is known, means moment of inertia of an object about its center of mass is known, then we can find the moment of inertia of that object about any other axis that is parallel to that axis. In other words, the parallel axis theorem is useful only to find the moment of inertia about an axis that is parallel to the axis through the center of mass. That's why it's called the parallel axis theorem. The new axis that we consider must be parallel to the axis that passes through the center of mass. Alright, now here I have an object. This is the axis that passes through the center of mass. And this is the new axis about which we need to find the moment of inertia. And this axis is at a distance h, the perpendicular distance between the new axis and the axis through the center of mass is h. So the figure shows an axis passing through the center of mass of the object and another axis that passes at a distance h from the axis through the center of mass. So the distance between that two axes is h. According to the parallel axis theorem, the moment of inertia I of the object of mass m about this parallel axis is I equal to I center of mass, that is moment of inertia about this axis that passes through the center of mass, plus mh squared, where m is the mass of the object and h is the perpendicular distance between the two parallel axes. Very simple theorem, but it is useful to remember because this is going to be used not only in physics 1 but also in physics 2. Very important to know that. Alright, let's use that in a situation. Find the moment of inertia of the ruler of negligible thickness shown in the figure about a perpendicular axis passing through its left end. This is a ruler of negligible thickness. Well, we know the moment of inertia of this ruler about an axis through its center of mass. Tell me, what is the moment of inertia of a ruler about an axis through its center of mass? What's the formula for that? It's 1/12 ml squared. In other words, I center of mass is 1/12 ml squared. If the length of the ruler is L and its mass m, the moment of inertia about its center of mass, about this axis, is I center of mass is 1/12 ml squared. we have been required to find the moment of inertia about an axis that passes through one of its ends. Alright. Since L is the length of the ruler, the distance between the axis through the end, if an axis is passing through an end, what is the distance between that axis and the axis at the center of mass? It will be half of the whole length. So H equal to L over 2. So this is the new axis. And for that new axis, this is H, the perpendicular distance between the two axes. And that H equal to L over 2. Alright, what does the parallel axis theorem say? It says the moment of inertia of this ruler about the axis through its end is moment of inertia about the center of mass plus mh squared. Alright, now I center of mass is 1/12 ml squared, there you are, plus mh squared, replace your h by L over 2. So that will be 1/12 ml squared plus m times L over 2 squared, and that will be 1/12 ml squared over 12 plus ml squared over 4. And what is that equal to? That will be 12 common denominator, that will be 12, it will be 3 ml squared plus ml squared, that will be 1/3 ml squared. So the moment of inertia of the ruler about an axis through its end is 1/3 ml squared, whereas the moment of inertia of that ruler about an axis through its center of mass is only 1/12 ml squared. And if you notice, this 1/3 ml squared is 4 times 1/12 ml squared. So if you want to rotate this ruler about one end, it's going to be very hard, because the moment of inertia of this ruler, you see, I can't even hold it there. The moment of inertia of the ruler about an axis through its end is 4 times the moment of inertia about an axis through its center of mass. Okay. Let's now talk about work done by a torque. Now, if you notice, for every term that we use in linear motion, there is a corresponding term in rotational motion. Tell me, what is work done in linear motion? In linear motion, work done is force multiplied by the linear displacement, F times x. So what do you think will be work done in rotational motion? Well, I'm sure most of you know it. Work done by a torque. You see, in the case of linear motion, work is done by a force when it produces a linear displacement. In rotational motion, work is done by a torque when it produces an angular displacement. So, work done by a torque is the product of the torque and the angular displacement. In linear motion, the work done is the product of the linear force and the linear displacement. Similarly, in rotation, work done by a torque is the product of the torque and the angular displacement. So W rotational is tau multiplied by theta. Work done by a torque results in rotational kinetic energy. Is that right? Whenever you do work on an object, that work will be a measure of the kinetic energy of this object. This rotating disc has a kinetic energy. How do you define that kinetic energy? The kinetic energy of a rotating disc is a measure of the work done to give it an angular displacement or an angular velocity. So this W equal to tau theta is a measure of the kinetic energy of the rotating disk. The disk on the right is rotating with an angular velocity omega. Consider a particle of mass mi at a distance ri from the center. Well, this is a particle of mass mi at a distance ri. I'm sure you understand this concept. If that is the first particle, the mass will be m1 and the distance will be r1. If it is the second particle, it will be m2 and r2. We will take a general case where we consider any particle called the ith particle. Its mass is mi and the distance of that from the axis of rotation is ri. Therefore, now if its tangential velocity is vi, if this particle has, of course, any object that goes around a circle has a tangential velocity. We call it the linear speed. If vi is its linear speed or the tangential speed, then its kinetic energy will be what? What will be its kinetic energy? 1/2 mi vi squared. So its kinetic energy will be Ki equal to 1/2 mi vi squared. Well, this can be applied to any particle on the disk. Alright? But Vi equal to Ri omega squared, is that right? The linear speed equal to R omega, V equal to R omega, not omega squared. You need to make that correction. Vi equal to Ri omega. The linear speed equal to R times the angular velocity. So if you now replace this Vi by Ri omega, what will become? What will be the expression for kinetic energy? Ki now equal to 1/2 mi. Vi squared become Ri squared omega squared. Ri squared omega squared. Well, the kinetic energy of the rotating disk is the sum of the kinetic energies of all the particles which make up the disk. This is the kinetic energy of one particle. Therefore, the total kinetic energy of the rotating disk will be the sum of the kinetic energies of all such particles. So how do we write the total kinetic energy? K rotation. K rotation is summation I 1/2 mi Ri squared omega squared. Well, this 1/2 is a constant. I can bring it out of the summation. Omega is a constant. For all particles, omega is the same. The angular velocity will not change. Just like alpha is the same, omega is the same for all the particles on the disk. That means that is a constant which we can bring out. This will be therefore 1/2 omega squared comes out. And summation I mi Ri squared. What is the name of this quantity? This is a special quantity. We gave it a name. What is that name? Summation I mi Ri squared is the moment of inertia of the rotating disk about an axis through its center of mass. So this is I, the moment of inertia of the rotating object. Therefore, what is the equation for kinetic energy? Kinetic energy of rotation is 1/2 I omega squared. Now, do you see any similarity between this equation and the equation for kinetic energy in linear motion? Now, look at the equation for kinetic energy in linear motion. K translational. Now, do you understand the meaning of translational? Translational is motion along a straight line. So K translation is 1/2 mv squared, and K rotation is 1/2 I omega squared. Now look at the similarities. What all we need to do is replace your linear velocity v by the angular velocity omega, and mass is replaced by I, its equivalent quantity in rotation. So kinetic energy in translational motion is 1/2 mv squared. Kinetic energy in rotational motion is 1/2 I omega squared. You can see the parallel nature of these equations make them very easy for you to remember, and you need to remember them. Okay. Let's now talk about the kinetic energy of a rolling object. Well, now what is the meaning of kinetic energy of a rolling object? Well, here I have a disk. I'm going to roll this disk. Now tell me, what are the type of motion it has? The disk is now rolling. Now, if you look at the motion carefully, it has two types of motion. What are they? It is rotating, and also it is moving along a straight line. Its center of mass is moving along a straight line. So when a disk is rotating, first of all, when a disk is rolling, it is rotating. That means it has kinetic energy of rotation. What is the equation for kinetic energy of rotation? K rotation is 1/2 I omega squared. So it rotates. It has a rotational kinetic energy of 1/2 I omega squared. And also its center of mass, this is the center of mass, and you can see the center of mass moves in a straight line with a linear motion. That means there is a translational kinetic energy 1/2 mv center of mass. It's the velocity of the center of mass that gives it the translational kinetic energy. So this rolling disk has two types of kinetic energies. It has a kinetic energy due to its rotation, 1/2 I omega squared, and it has a kinetic energy due to the translational motion of its center of mass, which is 1/2 mv squared, where v is the translational motion velocity of the center of mass. So a rolling object has both linear motion and rotational motion. When the disk rolls forward, its center of mass moves in a straight line with a velocity v center of mass. So this disk is rolling forward. Its center of mass will move forward with a velocity v center of mass equal to r omega. Are you familiar with that equation? Yes, v equal to r omega. So its center of mass will be moving forward with a velocity v center of mass equal to r omega, and it rolls on. It comes to a new position. That means it has been rolling from an initial position to a final position. Kinetic energy of this linear motion of the center of mass is called the translational kinetic energy. Kinetic energy of the disk due to its translational motion along the straight line. and that will be K translational is 1/2 mv center of mass squared, where v center of mass is the velocity of the center of mass, the linear velocity. The kinetic energy of rotation is, what is it? What is the kinetic energy of rotation? K rotation is 1/2 I omega squared. So what is the total kinetic energy of the rolling disk? K total, the total kinetic energy of a rolling disk is K translational plus K rotational. That is 1/2 mv center of mass squared plus 1/2 I omega squared. Now, have you ever tried stopping a tire that is rolling? Haven't you played with tires? If you try to stop it, you are sure to get hurt, because a rolling tire carries a tremendous amount of kinetic energy. It has the kinetic energy due to rotation and kinetic energy due to translation. And if you want to stop it, you need to do an amount of work equal to its kinetic energy. And that is a large amount of work. So you are sure to get some scrapings on your body if you try to stop a rolling tire. Alright, let's now talk about angular momentum. You see, notice we are picking one quantity after another, which we discussed in linear motion. In linear motion, we talked about linear momentum, and we represented it by P. P equal to mass times linear velocity, m times v. In the same way, an object in rotational motion has an angular momentum. Very important concept. The disk on the right is rotating about an axis through its center of mass. Here I have a disk, a very old disk, and I'm going to bring back my bunny now. So here I have a disk rotating about an axis that passes through its center of mass. And let's say it's rotating in the clockwise direction. The bunny is sitting at the edge of the disk, has a linear speed v and an angular velocity omega. Is that right? No problem there? It's got a linear speed v, means it describes a certain distance in a certain time, and it has an angular velocity omega. The radius describes an angle during the same time. What is the relation between v and omega? V equal to r omega. Okay, so the bunny has the linear speed v, and therefore its linear momentum p will be tangential. Is that right? The momentum is a vector which is in the direction of the velocity. So this is the direction of the momentum, and its momentum is p equal to mv, where m is the mass of the bunny and v is its linear velocity. So the linear momentum of the bunny going round and round is p equal to mv. The bunny has a momentum due to its rotation called the angular momentum, and the angular momentum is given by r times p. In fact, this is also a cross product. L equal to r cross p, r times p. Now, in this case, r is the radius and p is tangential. They are both at right angles. And therefore, we can say it is r times mv. If the angle between r and p is not 90 degrees, then it will become r times mv sine theta. But we will consider cases where the angle between R and P, the angle between R and P is 90 degrees. So the angular momentum, look at the representation of the angular momentum, it is L. Well, I told you some time ago that all the quantities in rotational motion is represented by Greek letters. Well, so far we represented everything by Greek letters. The only exception is the angular momentum, which we will use L. The angular momentum of a rotating object is represented by L, and that is equal to R times mv, where R is the distance of the rotating particle from the axis of rotation, and mv is its linear momentum. So R times the linear momentum is the angular momentum. R is the vector drawn from the axis of rotation, and P is the linear momentum. When R and P are at right angles, the magnitude of the angular momentum. Now remember, angular momentum is a vector quantity. It is given by the cross product of R and P. It's a vector quantity, it has a direction. But if you now consider the magnitude of the angular momentum, we can write as L equal to mv times R. And this is the magnitude when the angle between R and mv is 90 degrees. If the angle is other than 90 degrees, then you need to take the component at right angles to R. That will be P sine theta. Well, so the magnitude of the angular momentum is mvr. Okay. So the angular momentum of each particle, you see, I used a bunny over there to represent a particle. Now if you look at any number of particles on that rotating disk, the angular momentum of all those particles, or each of those particles, will be given by L equal to mvr, where m is the mass of that particle, v is the linear speed, and r is the distance of that particle from the axis of rotation. Alright, so here v is the tangential speed, and so on. The angular momentum L of the rotating disk, therefore, is the sum of all such angular momentum of all such particles. So how do I write it? It will be L equal to summation mvr. This is the angular momentum of just one particle. If you now add up the angular momenta of all particles that make up the disk, that will give you the angular momentum of the rotating disk. So L equal to summation mvr, and we can now replace this v by another quantity. Well, since we are looking at rotation, that quantity will be in terms of omega. V equal to r omega. So that will be summation mr omega times r, and r times r will be r squared, and omega is a constant for all particles on the disk. Omega is the same, so we take that omega out. That's equal to omega times summation mr squared. Well, now tell me, what does summation mr squared give you? Summation mr squared is the moment of inertia of that disk. So what does therefore angular momentum is? Summation mr squared equal to I, the moment of inertia of the disk. Therefore L equal to I, this is I omega. L equal to I omega. The angular momentum of rotational motion is I omega, where I is the moment of inertia of the particle about the axis of rotation and omega is its angular velocity. Now, how does it compare with the equation for linear momentum? You know that linear momentum P equal to mv and angular momentum L equal to I omega. I hope now you are able to appreciate the parallel nature of this. The linear momentum P equal to mass times linear velocity, angular momentum L equal to I, the moment of inertia, times angular velocity omega. So, we have now covered practically all aspects of rotational motion. For every quantity we discussed in linear motion, there is a corresponding quantity in rotational motion. We need to put all these things together to consolidate your understanding in order that we may solve problems. Let's now talk about conservation of angular momentum. Well, if linear momentum is conserved, angular momentum also should be conserved. Now, just like linear momentum, angular momentum L is conserved. Now, let's consider a disk like this. The disk on the right has a moment of inertia I1 and it is rotating with an angular velocity omega I or omega 1. So its moment of inertia is I1 and its angular velocity is omega I or initial angular velocity. Now its angular momentum is L1I equal to I1 omega I. Is that right? Its initial angular momentum at this time is its moment of inertia I1 times its initial angular velocity L equal to I omega. L1I equal to I1 omega I. A second disk of moment of inertia I2 is shown above. Here it is. Now this has a moment of inertia I2 and it is initially at rest. Now, have you ever seen one of those old record changers? When a record is going round on a turntable and it is nearly finished, you can allow the second record to fall on it. That means the second record is initially at rest. Its angular velocity is 0. It's now going to fall on the record that is already turning. That is the situation here. So here we have the first disk rotating with an angular velocity omega I. It has an angular momentum L1I equal to I1 omega I. And here we have a second disk which is now going to be dropped onto this first disk. What is the angular momentum of this disk before dropping? L2I equal to 0. Therefore, the total momentum of these two disks now is I1 omega I, the angular momentum of this disk, plus 0, because that has no angular momentum, it is not rotating. The total angular momentum Li, initial angular momentum, is I1 omega I. Okay. If disk 2 is now allowed to fall onto disk 1, the two together now will rotate with an angular velocity omega f, so that the final angular momentum will be, can you write what the final angular momentum will be? When this disk falls onto here, the two together are going to rotate. That means the total moment of inertia now is I1 plus I2. I2 is the moment of inertia of the second disk. So the final angular momentum is therefore I1 plus I2 omega f. You see, the total angular momentum is now I1 plus I2 omega f. Now, according to the conservation of angular momentum, the total initial angular momentum must be equal to the total final angular momentum. Is that right? That means I1 omega I must be equal to I1 plus I2 omega f. Now, this has wide applications and a very, very useful relation. The conservation of angular momentum. I'm sure you have seen a skater, well, going round in circles, is that right? Spinning like this. Now, how do they do that? Now, what they do is they first keep their arms apart like this so that they have a greater moment of inertia. You see, the moment of inertia of an object depends on its, well, remember, this is the axis of rotation if I rotate. Now, moment of inertia is mr squared. That means if my hand is over there, this part of my hand, the moment of inertia will be this mass times this r squared. So if I keep my arms outstretched, I am increasing my moment of inertia. So if I start spinning with my arms like this, I have an angular momentum. What will be my angular momentum? My angular momentum, I'm going to call it I initial, will be I omega. I'm going to call it angular momentum L initial equal to I1 omega 1. My initial angular momentum is I1 omega 1 or I sub I omega I, initial angular velocity. Now, as I keep doing this, what happens if I bring my arms close to my body? I'm reducing my moment of inertia. So, when my arms are closer, my angular momentum at that time, LF will be IF omega F. Now, the moment of inertia when my arms are close to my body will be smaller than the moment of inertia when my arms were outstretched. That means you know that the conservation of angular momentum dictates that Li must be equal to Lf. That means I omega I must be equal to IF omega F. Now this is very significant because when I bring my arms closer, my moment of inertia IF becomes smaller, and in order that the angular momentum may be conserved, my angular velocity must increase. So if I start off like this, when I bring my arms I go very fast, and that is what these skaters actually practice. So conservation of angular momentum has great applications. Well, if you now put all these together, what have we done in this lesson? We discussed practically all quantities in rotational motion that we used in linear motion. Is that right? torque equal to I alpha, F net equal to ma. The angular momentum L equal to I omega correspond to P equal to mv. Kinetic energy for linear motion 1/2 mv squared. For rotational motion 1/2 I omega squared. And what is the kinetic energy of a rolling object? 1/2 will be kinetic energy of rotation and the kinetic energy of translation 1/2 mv squared plus 1/2 I omega squared. Well, so put all these things together. I'm going to do another lesson. Using all these, we will solve problems. All right, I will see you for that later on.